We present Mesh4D, a feed-forward model for monocular 4D mesh reconstruction and tracking. Given a monocular object-centric dynamic video as input, we want to reconstruct a sequence of textured 3D meshes with dense correspondences. On the right, we show the 4D reconstruction output produced by our method, seen from two different viewpoints. To train a diffusion-based reconstruction model, we first need to build a 4D variational autoencoder that encodes the deformation field in a compact latent space. Given a sequence of 3D meshes as input, we first uniformly sample a sequence of corresponding points. Then we leverage position embedding and project it into higher dimension. We inject the skeleton information by using masked self and cross-attention. Then, a farthest point sampling, FPS, at spatial dimension is performed to compress the latent, followed by 8 layers of spatiotemporal attention. The deformation field is decoded by layers of spatiotemporal attention, followed by a cross-attention where canonical vertices serve as query points. Each of our spatiotemporal attention layers sequentially performs temporal attention, global attention, and spatial attention. The encoded deformation latent is used as target for the deformation diffusion model. We start from a noisy latent sampled from a Gaussian distribution. We add the temporal embedding and spatial embedding from the canonical point cloud. A skip connection is added in the DIT block to preserve the information from previous blocks. Video conditions are injected in the cross-attention layer using DNO features. Canonical shape condition are also applied by the cross-attention with its vector set feature extracted from HY3D shape VAE. We first show results for novel view synthesis and tracking. We compare our approach with 3 state-of-the-art methods, HY3D, GVDF and L4GM. Frame-wise reconstruction methods, like HY3D, produce inconsistent shape and texture. Our method avoids predicting extremely incorrect canonical mesh by leveraging a large-scale reconstruction method. All the state-of-the-art methods suffer from inaccurate pose estimation, for example for the limbs of the mantis. This is due to a lack of temporal attention or to the absence of geometric supervision. Similar errors, such as inconsistent shape and texture and inaccurate pose estimation also appear in this other example. 3DGS-based methods occasionally exhibit ghost artifacts due to a lack of topological and geometrical constraints during training. Thanks to the geometric constraints, skeleton information, and spatiotemporal attention, Mesh4D is able to reconstruct accurate pose and geometry, and produces temporally consistent novel view video. To better assess the quality of the estimated geometry, we also visualize the normal maps. Even if the canonical mesh is not exactly accurate, we can still reconstruct physical plausible and reasonable motion. On the contrary, the HY3D model often produces inconsistent shapes even if we apply shared noise to different frames. Here we show more reconstruction results. Our method generalizes well to different types of dynamic objects, including human, humanoids, animals, and monsters. Our model can also generalize very well to in-the-wild monocular videos. Here, we show some reconstructed results from the in-the-wild consistent 4D dataset. Thank you for watching.